All right, let's dive right in. Today, we're tackling a question that seems impossible. What is the square root of -1? The answer unlocks this hidden two-dimensional world of numbers that are absolutely essential to things like physics and engineering. We're going to demystify complex numbers, and I promise you are never going to look at a number line the same way again.
So let's just kick things off with a question that kind of flips everything on its head. What if a number wasn't just a point on a line, but a location on a map? What if one single number could describe both how far to go and which way to turn? That's the core idea we're digging into today.
So here's our game plan. First, we're going to invent a number that shouldn't even exist. Then, we'll find a home for it, not on a line, but on a whole 2D plane. We'll learn its rules for adding and multiplying, uncover its secret mirror image, and finally, see how it all simplifies in this really beautiful way when we look at numbers that live on a perfect circle.
Okay, part one, imagining a new number. You know, for centuries, mathematicians were just stuck. They had positive numbers, they had negative numbers. But what happens when you try to solve an equation like x squared equals -1? You can't. Well, not unless you invent something totally new.
So, say hello to the complex number z. It's got two parts. The first part, x, is a real number, the kind we use every single day. The second part is the imaginary part. It's another real number, y, but it's multiplied by the star of our show, the letter I, the imaginary unit. And I is simply defined as the number that when you square it gives you -1. It's the solution we were looking for. And this right here, this is the key takeaway. To define just one of these complex numbers, you actually need two regular old real numbers, an x and a y. Think about that. It's a single number, but it's carrying two pieces of information inside it. That is a huge deal. Keep that in mind, because it's going to be important.
So if these numbers need two pieces of info to exist, where do they live? Well, that brings us right to section 2, plotting on a new plane. This is where we go from some abstract algebra to something we can actually see.
See, since a complex number has two parts, x and y, it just can't live on a simple number line. It needs more space. It needs a plane, what we call the complex plane. The horizontal axis, that's for the real part. And the vertical axis, that's for the imaginary part. All of a sudden, our number isn't just a value anymore. It's a specific location. We've made this huge leap from a formula to a map. Now, how do we actually find a point on this map? Well, there are two classic ways. The first is called Cartesian, and it's basically like city grid coordinates. Go x blocks east on the real axis, then go y blocks north on the imaginary axis. Simple. The second way is polar. This is more like giving directions from a landmark. You stand at the center, face in a specific direction, we call that angle theta, and then you walk for a certain distance, r. Two totally different sets of instructions that lead you to the exact same spot. Okay, so we know what they are and we know where they live. Now let's see how they actually play together. Section 3, the rules of combination. And this is exactly why having two different address systems is so incredibly powerful. If you need to add two complex numbers, that grid-like Cartesian form is perfect. You just add the x parts together and you add the y parts together. Easy. But if you want to multiply them, oh, that's where the polar form is an absolute lifesaver. You just multiply their lengths, r, and add their angles, theta. It turns what would be a really messy process into simple arithmetic. Now, this formula might look a little intimidating, but don't worry, it's just the mathematical way of saying what we just said. Multiply the lengths, r1 times r2, and add the angles, theta 1 plus theta 2. This shows us what complex multiplication really is. It's a combination of scaling and rotation on that complex plane. It's a stretch and a spin. All right, now for a deeper, kind of profound idea. Section 4, the mirror image or conjugates. It turns out every single complex number has a sort of twin. On the left, you've got our original number, z, and on the right, you have its complex conjugate, which we call z star. The rule is incredibly simple. You just flip the sign of the imaginary part. That's it. So plus iy becomes minus iy. On our complex plane, this is just like creating a perfect mirror image right across the horizontal axis. So why is this mirror image so important? Well, check out what happens when you multiply a number by its twin. The imaginary parts, the plus iy and minus iy, perfectly cancel each other out. And you're left with something incredibly simple and familiar. A single, positive, real number. Specifically, you get the square of the number's distance from the center,
r squared. It's like a magic trick for collapsing two dimensions right back into one. And this is more than just some neat math trick. The source material suggests we should think about this more deeply, that the set of all the z numbers and the set of all their z-star partners are like two separate but intimately connected dual number systems. For every number in one, there's a unique partner in the other.
Now, for our final piece of the puzzle, and this is where things get really elegant. Section 5, the power of phase factors. This is a special case that simplifies everything we've just learned.
A phase factor is really just a complex number that lives on a perfect circle with a radius of exactly 1. Its length, its r component, is fixed at 1. And that means the only thing that can change about this number is its angle, theta. It's a pure rotation. And when that length r is locked in at 1, everything becomes beautifully simple. Multiplying a number by its conjugate just gives you 1. The polar form slims down to just e to the I theta, and this formula, which is the famous Euler's formula, reveals a stunning connection between imaginary numbers and the trigonometry of circles, linking it all to cosine and sine. It's truly one of the most beautiful equations in all of mathematics.
So we'll end with this thought. We started with a simple number line and discovered this whole two-dimensional world with its own rules, reflections, and dualities. The source called conjugates, part of a dual number system, which really makes you wonder, what other secrets, what other dimensions might be hiding in the numbers we think we know so well?
All right, welcome to The Explainer. Today we are diving into a concept that completely flips our understanding of reality on its head. We're going to move from thinking about the world as a simple list of possibilities to the incredibly strange, abstract world of quantum states. It's a journey from sets to spaces. So, just think about the world around you for a second. You know, a light switch is either on or it's off. A coin flip gives you either heads or tails. It feels totally obvious that reality is just a collection of distinct states, right? It's one thing or another. Well, it turns out that on the most fundamental level, that simple, intuitive idea is just completely wrong. See, the quantum world doesn't play by either-or rules. It has a completely different operating system, and that's exactly what we're here to unpack. Okay, so let's jump right into the first huge idea, the massive, fundamental difference between how classical physics, the world we actually see and interact with, and how quantum mechanics describes the universe of possible states.
So in our normal, everyday, classical world, states are just a set. It's basically a simple list. On, off, heads, tails. But in the quantum world, it's not a list, it's a vector space. And the biggest shift you have to make in your head is moving from thinking about a list of things to a space of directions. This is so important because it allows quantum states to be combined, to overlap, to interfere with each other in ways that are just impossible in our classical world.
Now, to really get this, we have to do something that's going to feel a little weird. We need to take a concept we all think we know really well and just unlearn it, to make room for a new, way more powerful idea. When I say the word vector, I bet this is what pops into your head. An arrow floating in 3D space, pointing in some direction, and it has a certain length. It's got those three components, right? Up, down, left, right, forward, backward. And for the world we live in, that's a perfect way to think about it. We call that a 3-vector. But, and this is a big but, for where we're going, you need to just put that idea aside. Seriously. If you hold on to that picture of a 3D arrow, it's actually going to stop you from understanding what a quantum vector really is. Because a quantum vector is a totally abstract object that might have nothing to do with ordinary space at all. Okay, so with that old, familiar idea out of the way, we can finally step into the new landscape. It's time to meet the stage and the players for all of quantum mechanics. This is our new environment, Hilbert space. Now, this isn't physical space. It's a purely mathematical space. Think of it as a giant container that holds every single possible state a quantum system can be in. And unlike our 3D world, a Hilbert space can have any number of dimensions, 4, 5, 1,000, even an infinite number of them. This is the arena where quantum reality actually happens. And who are the players in this space? Well, they're called ket vectors, or usually just kets for short. You can see the weird notation there with the vertical line and the angle bracket. A ket, like this one labeled A, is our new, more abstract kind of vector. It doesn't point somewhere in our room. It represents a very specific quantum state. So, we have these kets, and they live in this Hilbert space. What can they actually do? Let's check out the basic rules of the road. The official math behind it can look pretty complicated, but it really boils down to a couple of simple ideas. The rules are actually pretty intuitive. First, you can add any two quantum states, any two kets, and the result is another perfectly valid quantum state. Simple enough. Second, you can multiply any ket by a number, and this basically scales or rotates it around in that abstract Hilbert space. These two rules together are what physicists call linearity, and they are the absolute bedrock of quantum mechanics. They make sure everything is consistent and predictable.
All right, we've built the stage, we've defined the characters and their rules, but now we come to the single most important detail. The one thing that separates the quantum world from our own, and the very thing that makes this whole framework so powerful and so weird.
This right here, this is the whole game. Remember our old 3 vectors? You multiply them by plain old real numbers to make them longer or shorter. But kets, our quantum states, you can multiply them by complex numbers. Now the key thing to know is that a complex number doesn't just stretch or shrink a vector, it can also rotate it. This ability to rotate states in an abstract space, that's the magic key.
And that's the core of it all. That one difference, the fact that we're allowed to use complex numbers, that is everything. It's the reason quantum states can interfere with each other. It's why they can exist in these weird superpositions. It is the fundamental reason that reality at the smallest scales is a complex vector space and not just a simple checklist of options.
So think about where we've ended up. We've gone from a simple list of states, on or off, to this infinitely complex vector space where states are just directions. And that leaves us with a pretty profound final thought. If the fundamental states of our entire universe are really just vectors in some abstract mathematical space defined by complex numbers, what does that even mean for our definition of what is real?